Okay everyone, I'm back. Just wanted to put out a quick little video about the Zener diodes. And so what we have here is we have a diode that looks very similar to your normal diode, but instead we've got little flags coming up on either side of the cathode, denoting that it's a Zener. We still have the cathode or the negative at the dash or the line. We still have the positive and the anode. But what's different about our Zener than about our regular diodes is that they can conduct in both directions. And they're meant and designed for that purpose. So if we were to take a look at some of our diodes in a circuit, we're going to see that how they behave differently. So I wanted to compare and contrast 4 circuits: our go, no-go, or our forward and our reverse biased regular diode, and our forward and reverse biased Zener. Okay. Okay, so before we get into our circuit, though, I want to quickly look at remembering how the PN junction works in our regular diode. When we have a diode that is forward biased, we have current flowing this direction, around our circuit. This is our battery symbol. They didn't draw multiple cells, they just drew one cell. The negative is right here, positive is right here. The current is flowing counterclockwise around this. Our negatively doped region is here, our positively doped region is here. We naturally have more electrons, and we naturally have fewer electrons or more holes for electrons to flow over here. When this battery is hooked up, it starts wanting to push electrons through the diode in this direction. And because of the way the diode is constructed, it's happy to do that. If, however, we try to go in the opposite direction with all of our current, and we want to go counterclockwise, then what we're going to find is we get stopped. And that's what's happening over here on the reverse bias side. We have our battery turned around, so the negative is making our current go this direction, and it can't do that. The positive region sort of attracted to, and the electrons that are in here are being attracted this direction, so there's not a flow that can happen here. And that's a trouble for our diode. Our depletion region becomes larger. Our extra electrons that are over here, they actually are attracted to the top part of this battery. They want to go this way. Our extra electrons in the battery are attracted over here. So this depletion region just grows. It makes it impossible for us to conduct. Okay, so when we look at a regular diode's curve, we can see that in our response. As the voltage increases here, so as the voltage, let's hop over into this program. As the voltage increases, we'll just point here. As the voltage increases, we eventually start to conduct right here in this knee region until we're conducting at 0.7 volts for silicon or 0.3 volts for germanium. And once that diode fully opens up, it will conduct more current. You can see that here I've got the current is going up, straight up. Even if, well, we can't apply more voltage to it, and I'll explain that in a minute. We can, but that would cause a problem. If we go to the left, or reverse bias, we see that our diode conducts a little bit of current in reverse, but it's really pushing back against what wants it to do that. But eventually, if we push it too hard, it will break down. These Zeners don't break down and recover. They're not like a fuse. They just break, and they might blow to an open, or they might short out, but typically you see them cook and they won't conduct anymore. So that is our normal diode here. You can see once again the engineers have decided that they're going to tell us the direction that current flows from positive to negative. That's wrong. Please ignore that. Holes don't flow. All right, so then if we take a look at the next portion of our sheet here, we look at how a Zener behaves. Okay, what a Zener does is it can conduct in either direction. So it has its normal diode curve where if it starts to be forward biased over on the right side of our graph in quadrant 1, we can see that knee current starts up, and we can see it actually increase until we get to our 0.3 or our 0.7, and it will conduct more current, but it's going to hold. It's going to hold at this 0.7 or 0.3 volts, depending on if it's 0.7 for silicon, 0.3 for germanium. When we get over to the left-hand side, we are going to start to be in first, depending on what type of diode we have, Zener or avalanche mode, but let's just call it Zener voltage for now. To the left, we see that we can start to conduct a little bit of voltage that eventually, when that diode opens up, it's going to continue to dump current, and it's going to want to hold at its Zener voltage. Zeners come in a wide range of design voltages. They can be down to underneath of a volt, or they can go all the way up to many volts. There are Zeners. You can find them in 5.1, 4.7. There's a standard range of sizes that used to be manufactured, and those are typically cheaper, but you pay a little bit of extra money, you can get almost any value that you want. And they can be good if you want to hold a certain voltage in your circuit at a certain place. Resistors have a tendency to, if the voltage fluctuates, they have a tendency to change their value a little bit. Depending on where we connect signal or output voltages, we may see those reference points change a little bit. So one way to make sure they don't change is to put a Zener there in series with a current limiting resistor. Our current limiting resistor value will change if the overlying voltage of the circuit changes, but the Zener will remain the same, and it will shed more or less current and do what it needs to do to maintain its voltage in its Zener mode. Now let's take a look at our diode and our Zener in the forward bias mode. First we have our regular diode. We know that it's negative, positive, so it's a go, first of all. Alright, and then up here we have a resistor, and I'm going to say that's 1K, so we'll call this R1 D1. Okay, at R1 we need volts, we need amps, we need resistance. I know it's 1 kilo ohm because I said so. I don't know the voltage yet or the current. I have to see if my diode is going to turn on first. So I determined that it's a go, and I determined that it has enough current. I've got 10 volts here. It's got to be more than 0.7. So I know that my diode turned on. So I have 0.7 volts. What's my current of my diode? Well, I don't know my current of my diode. I have to hear that from the resistor. Okay. So the next step of the puzzle here is I have 10 volts in my battery. If I bring this around, red lead, black lead, I know I have 10 volts up here. 0.7 is going to this diode, so the remainder, 9.3 volts, has to go to the resistor. Okay. Now, I know my voltage and my resistance up here in my resistor. So, does my diode turn on or not? Yes, it does. Now I know my resistor, at least in this circuit, takes the rest of the voltage. So I have 9.3 milliamps. 9.3 volts divided by 1,000 ohms is 0.0093 amps, or 9.3 milliamps. Okay, so now I know that I have 9.3 milliamps here at my diode. That makes my resistance 0.7 divided by 9.3. I get out my calculator and I do 0.7 volts divided by 0.0093. I get 75.27 ohms. Okay, so step number 1, is my diode a go? If it is, great. It's greedy, it takes its voltage first. Step number 2, I give the rest of the voltage to the resistor. Then the resistor in turn tells my diode how much current it's going to get. You are going to get my voltage divided by my resistance, which is 9.3 milliamps. 9.3 milliamps comes down here, 0.7 volts, 9.3 milliamps. Now I can figure my resistance here. Okay? Now, let's take a look at how the Zener behaves in that same situation. Okay? Here I have my Zener. My 10 volts comes along. Okay? I have a negative, positive, positive, negative. It's a go. It's going to give me 0.7, or at least this Zener is. So I get 0.7, 9.3. R1, R2, or excuse me, D2, R2. God, it's getting late. It's getting late. R2, D2, R2, D2. Volts, 9.3 volts of R2. Okay. Volts, D2, 0.7. Okay. What's my current? Current, 9.3 milliamps. same as before with the regular diode. Okay, because my resistance is 1K. Okay, again, 1K, 1K, same voltage, same current, 9.3 milliamps. So then my resistance is, I don't remember my number, but we can just do the math again. Oh, here's some on my calculator. 0.7 divided by 0.0093, that's going to be 75.27 ohms. So it just does the same thing. It's forward biased. Let's take a look at what happens if we reverse bias. Okay, forward is our go, reverse is our no-go. So let's draw a regular diode in series with a resistor. Diode always has to be in series with something resistive. It'll take as much current as you'll give it, and they all come with a maximum current. So if you just let them take all the current, they're going to blow up. Okay, so this one's easy. Internally, here's our cathode, here's our anode, here's our cathode. Bring our voltage around. Here's my poorly drawn resistor up here. It looks more like a scribble. But this never even comes on. My positive volts comes around, my negative volts comes around. This is a no-go. Doesn't go. Acts just like an open switch. 10 volts here, 0 volts here. Open. Can't conduct. Okay? So then we go over to the Zener. What's going on at the Zener? This Zener is going to have a value. So this is 1K, this is 1K. We'll keep it all the same. The Zener is going to come with the Zener voltage value. And I'll just say it's 5.1 volts right now. But they can come in all sorts of different values. All right? I come around here. I know that I have negative, positive at my Zener. And I have positive, negative. They don't match. We said that that was a no-go for a regular diode, but for a Zener, that just means now it's going to be in Zener mode. Or they call some modes for Zeners avalanche, but we'll just stick with Zener mode for right now. Okay? I drew this wrong. Doggone it. Negative, positive. So that would normally be a no-go, but in this instance, it's Zener. It's go Zener. Okay? So we said the solid-state devices take their voltage first. They don't go, and they're open. If they do go, well, then they take whatever their voltage is. So in this case, we have V of D2 equals 5.1. I don't know anything else about it yet, but I know it takes 5.1. That means R2 must take 4.9. Okay, that takes 4.9, and my resistance is 1K. That must be my current is 4.9 milliamps. Okay, if I have 4.9 milliamps here, I have to have 4.9 milliamps here. And so then the question is, what is 5.1 volts divided by 4.9 milliamps? And that gives me resistance of 1.041 kiloohms. So in our last example, our Zener had 75 or something like that ohms. Here it's got 1.04. What is happening in this reverse mode? Okay, in this reverse mode, whatever I put up here for a resistor, that's going to dictate what the current is. That resistor, it can't lie. Whatever its voltage and its resistance are, that's what the current must be. But the resistor gets its voltage from the Zener. Whatever that Zener value is sets the voltage for the bottom half of this series circuit. Once it sets the voltage for this portion of the circuit, the rest of the voltage must go to the resistor. Then the resistor can figure out, based on its resistance and the voltage that it's given, what current that it's going to pass through the rest of the circuit. It then passes or limits the current back through, and our Zener then, having voltage and now current, we know the resistance of it. This will variably resist based on how much current that resistor gives it. I hope that gives you a little bit of a background on how Zener diodes work as opposed to regular diodes. It starts to cement in some of those characteristics of what we see happening when we're doing our circuit analysis.